The objective of this lecture is to provide the first part of the study of the two-body problem. This lecture focuses on the two-body differential equation and the derivation of the orbit equation. This lecture will be divided into the following parts. First, the two-body problem is stated physically. Second, the differential equation that describes the motion of a spacecraft relative to a planet or relative to a central body is derived. And third, the two-body differential equation, as we will call it, is solved. And we'll get into the details of what we mean by solving the differential equation as we move through the lecture. And fourth, key properties of the two-body problem are derived along the way. We'll actually have some properties that we'll derive as we move through the lecture. So now let's get started with the two-body problem. So this is a physical description of the two-body problem. So the two-body problem is shown schematically as follows. So we have an inertial reference frame, which will be denoted I. And we have two objects that are moving relative to that inertial reference frame. So I have a point O, and O is fixed in I. And I have, as I said, two objects. The first object I'm going to call big M. It's a particle. They're both going to be modeled as particles. So I'll have a particle big M. The second object is a particle that I'm going to model as little m. And the position of the first object is going to be denoted R sub big M, and the position of the second object is going to be denoted R sub little m. And these positions are both measured relative to this point O, which is fixed in the inertial frame. And then I have the position of little m relative to big M. And this position is going to be defined as just R, which is going to make things a little bit easier. So let's write this down. So Rm is equal to the position of big M relative to O. And R little m is equal to the position of little m relative to O. And finally, R will be defined as R little m minus R big M, which is also equal to the position of little m relative to big M, and that's the relative position. So we'll call that the position of little m relative to big M. Now, in order to be able to sort of identify what these two masses are, the following terminology is going to be used. So we're going to say let big M be what's called the central body. Sometimes that's also referred to as a planet, although it need not be a planet. So I'm just going to refer to it as the central body. Little m is going to be the spacecraft. So what we really have in this situation is we have motion of a spacecraft under the influence, and I should say the gravitational influence of a central body. And this is a big assumption that we're making here. So we're going to assume all other forces are negligible. And what that means is that there could be other bodies in the system. There usually are. We're going to ignore the effects of those bodies. There could be other forces. There could be things like drag, radiation pressure, other kinds of things, the physical effects. We're going to ignore all of it. So the only thing that's going to matter is that the spacecraft is under the influence of this one central body. And now what we're going to do is we're going to derive the differential equation that describes the motion of this system. So this problem that we have here, this is what's called the two-body problem. It's a two-body problem because there are only two bodies in the system. So from this point forth, we're going to refer to it as the two-body problem. So we can see that the only forces that are being exerted on either of the bodies is the gravitational force of the other body. So the force exerted on little m is due to gravitation by big M. So that implies that the force exerted by big M on little m, this is equal to the force exerted by big M on little m, has to equal minus g times the product of the masses, all divided by r cubed times r, because r is the relative position between the two, and little r is going to be the magnitude of that position. So we're going to actually put this, we'll put this here just so that you can see it. We'll say let little r equal the magnitude of r. Now that's just gravitational force. It's inverse square gravitation, which is what we had derived in an earlier lecture from Newton's universal law of gravitation. So then the force exerted by little m on big M, so this is the force exerted by little m on big M, is equal to minus the force exerted by big M on little m. So that's equal to g times the product of the masses, all divided by r cubed times r. And because these are the only two bodies in the system and there are no other forces, we can now apply Newton's second law to each body. So applying Newton's second law, to little m, we have that the force exerted on little m has to equal the mass times the acceleration in the inertial frame of little m. So that implies that the force exerted by big M on little m has to equal the mass times the acceleration of little m, which implies that minus g times the product of the masses divided by r cubed times r has to equal m times the acceleration of little m and I. Now you'll actually see that the other application of Newton's second law looks almost exactly the same, which is applying Newton's second law to big M. We have that the force exerted on big M has to equal the mass, which is big M, times the acceleration of big M in the inertial frame. So that implies that the force exerted by little m on big M has to equal big M times the acceleration of big M in I, which implies that g times the product of the masses, all divided by r cubed times r, has to equal the mass times the acceleration in the inertial frame of big M. So we now have both of these, and we can actually use these equations in tandem to be able to derive the motion of the spacecraft relative to the planet. So first, suppose I take this first equation and I divide. So here's what I'm going to do. I'm going to divide by little m. What do I get? Well, I get the acceleration of little m and I is equal to minus g times big M all divided by r cubed times r. Let's do the same thing with the second equation. But this time, I'm going to divide by big M. So then I get that the acceleration of big M in I is equal to g times little m all divided by r cubed times r. So now you can see that I have the acceleration of each body individually due to the forces, or the force in this case that's applied to that particular body. So then we can actually subtract these two equations to get the acceleration of little m relative to big M. And we'll do that next. So then the acceleration of little m minus the acceleration of big M in I has to equal minus g times big M all divided by r cubed times r minus g times little m all divided by r cubed times r, which of course I can now add these together. But before I do, we're going to say let the acceleration of little m minus the acceleration of big M equal the acceleration of little m relative to big M in I. But we know that that's just equal to the second derivative in I of the position that we started which is the position of little m relative to big M. But we just called the position of little m relative to big M, we just called it r. So recall that the position of little m relative to big M was defined as r. So that means that the acceleration of little m in I minus the acceleration of big M in I is just equal to AI, because the notation would be consistent, right? So that has now got to equal, well, if I take these two terms on the right-hand side, I get minus g times big M plus little m, all divided by r cubed times r. So now here's where the next assumption comes into play, is that recall that big M is a central body, which we also referred to as a planet, while little m is a spacecraft. So from a physical standpoint, it would be clear that the planet, or the central body, would be much larger in mass than the spacecraft. So we're going to assume the following, which is that the mass of the central body is much, much bigger than the mass of the spacecraft. So that implies that m plus little m is approximately big M. So we're just going to replace m plus little m with big M in this equation, and that gives us that AI is equal to minus g times m over r cubed times r. Now this is an approximation, but we're going to treat it as an equality. And we're actually going to use this approximation in the remainder of this material, which is that now we're going to do the following. We're going to actually make a substitution here, and we're going to use that substitution to be able to make this equation look a little bit cleaner than what it is right now. So we have the acceleration of the spacecraft relative to the planet is equal to minus gm all divided by r cubed times r. Now what we're going to do is we're going to say let mu equal g times big M. And this is going to be defined as the gravitational parameter of the central body. So if we just replace gm with mu, we get that AI, which is the acceleration of the spacecraft relative to the planet, is equal to minus mu over r cubed times r, which gives AI plus mu all divided by r cubed times r equals 0. This last equation is what's called the two-body differential equation. And what's important about this equation is that the two-body differential equation describes motion of a spacecraft relative to a central body, where it is assumed that the central body is significantly larger in mass than that of the spacecraft. Now, that assumption actually allows us to be able to do something else, which is really important. So let's go back to the original diagram, and we'll see something here that actually makes this a little bit more tractable. So originally, we had the following diagram. We had this inertial frame, and the inertial frame had a point O, which was fixed in I. So it's sort of a repeat of what I had written earlier. And then we had these two objects. We had little m, big M, and then we had the position of the spacecraft relative to the central body. So here was M, and here's little m, and this was the position of big M, and this is the position of little m, and this was the position of little m relative to big M, which was just equal to r. Now, because M is much, much bigger than little m, it is reasonable to approximate. This is an approximation, but it's a good approximation. M as being an inertially fixed point. Now, it's not an inertially fixed point because you can see in the diagram that O is the inertially fixed point. But we're just going to make that assumption. So in other words, we're just going to move the inertially fixed point, which is at O, we're going to make it the same as M. So what we're going to do is we're going to say, let M be an inertially fixed point, and denote this point as O. So we're just kind of going to move everything so that big M is now actually O. So when we do that, we get the following diagram, which simplifies things, which is that the new diagram has O here, still an inertially fixed point. So O is fixed in I, but now M is actually located at O. So I just have M and I have little m up here. and then here's my position r. So that's a simplified diagram based on the fact that I now am assuming that big M is an inertially fixed point. So then the next step is to solve the two-body differential equation. So we now have the differential equation that describes motion of a spacecraft relative to a central body. So now the next thing is we want to solve this differential equation. Now, what's really important about this differential equation is that it cannot be solved as a function of time. So this is a very important aspect. The two-body differential equation cannot be solved analytically as a function of time. In other words, we can't get the position as a function of time. What we can do is we can get the solution as a function of an angle. And I'm going to go through this in some detail right now. So instead, the position of the spacecraft can be determined as a function of an angle. Now, what's really important is what we're really getting is we're going to get the radius as a function of angle, of an angle. So actually, the radius can be determined as a function of an angle. And that actually is equivalent to the position, but we actually are getting the radius, and we'll see that why it's equivalent to the position when we're actually done with all of this. So in order to be able to get started with this, what we really need to do is we need to be able to quantify this differential equation, because this differential equation is coordinate free. We haven't laid down any coordinates yet. So as of yet, no coordinates have been used. So in other words, the two-body differential equation is coordinate free. So in other words, the two-body differential equation itself is coordinate free. But we need coordinates in order to be able to do this. So in the process of solving this problem, we're going to develop a coordinate system. So now, as part of solving the problem, so as part of solving the two-body differential equation, a coordinate system will be developed. So now let's start this whole process. So recall that the two-body differential equation is AI plus mu over r cubed times r equals 0. So the first quantity I'm going to define is what's going to be called the specific angular momentum. So let HI equal r crossed with VI equal what's called the specific angular momentum. Now the specific angular momentum is the vector product between r and what's in there, VI, where VI is the inertial velocity of the spacecraft relative to the central body. So now that we know that, let's discover some properties of this specific angular momentum. So take the rate of change of HI in the inertial frame. So what do we get when we do that? We've got d dt in I of HI. But HI is r crossed with VI. So that's d dt in I of r crossed with VI. Now this follows the product rule for differentiation. So this is equal to the derivative of the first crossed with the second plus the first crossed with the derivative of the second. Well, the derivative in I of r is just VI. So we get VI crossed with VI. Plus, we get r crossed with, well, the derivative in I of VI. But the rate of change in I of VI is the acceleration in I. So this is equal to VI crossed with VI plus r crossed with AI. Well, VI crossed with VI is 0. So this just gives r crossed with AI. But from the two-body differential equation, AI is equal to minus mu over r cubed times r. So this gives r crossed with minus mu over r cubed times r. But minus mu over r cubed is a scalar, so I can bring it out front. So we get minus mu over r cubed times the position crossed with the position, which is equal to 0, because r crossed with r is 0. And notice that this step right here, this is from the two-body differential equation. So we now know that d dt in I of HI is 0. That implies that HI is fixed in I. So we now have a vector that is fixed in I. Now let's look at a little bit more about properties of this vector that's fixed in I. So we know that HI equals r crossed with VI. But r and VI together form a plane. And furthermore, this plane formed by r and VI contains the solution because R and VI together is the solution. In other words, the position, if I know the position, then I have the solution. If I know the position, I know the velocity, because the velocity is the rate of change of the position. So I know everything that I need to know in order to tell you what the solution is. So that means that R and VI form the solution plane. What that means is that there's a plane in which R and VI lie where the solution lies, and furthermore, HI is orthogonal to this plane. So what does that picture look like? It looks as follows. So if I go back to my schematic, I have this inertial frame I have this point O, which is fixed in I, and I have this vector, which has to be fixed in the inertial frame, which is HI, right? That's the specific angular momentum. And then there's a plane. Now this plane is the plane in which the solution lies. So this is the plane of the solution. So now I have a vector r, and I have a velocity v to go with r. So r is the position, and vi is the inertial velocity. And r and vi lie in the plane of the solution. And furthermore, we know that HI is fixed in I. So because HI is fixed in I, and it's orthogonal to the plane that contains R and V, and that plane is the plane of the solution, that implies that the solution plane itself is fixed in I. And that's really important. So that means that the plane in which the solution lies is inertially fixed, which is really an important part of this entire discovery of the properties. So now we have one vector which is fixed in the inertial frame, and that is the specific angular momentum. So once we have the specific angular momentum, we know it's fixed in I. We can now go after a second vector and figure out a second vector that's also fixed in I, and that will help create a basis for us. Because once we have two vectors, and assuming they're orthogonal to one another, we can take the cross product of them to get the third vector, and that third vector will complete the right-handed system, and we'll have a basis, and that basis will be fixed in the inertial frame, and then we can take all of our measurements relative to that basis. So that's the next step, is to figure out the next basis vector, and subsequently to get this basis in place. So now we have one vector that is fixed in I, and that vector is the specific angular momentum. So now return now to the two-body differential equation. So we have AI plus mu over r cubed times r is equal to 0. Now what we want is, we want a second vector that is fixed in I, And we want this vector the second vector to be orthogonal to HI. Now, why do we want it to be orthogonal? Again, we're trying to construct a right-handed orthonormal basis so we can figure out how to quantify the solution to this differential equation. So we need it to be orthogonal to HI. So in order to do that, let's take the vector product of the two-body differential equation with HI, and that looks as follows. We take AI plus mu over r cubed times r, and we take the vector product with HI. Well, that of course is still going to equal 0 because the two-body differential equation itself is equal to 0. Now what we're going to do is we're going to split this up into two parts. So we get AI crossed with HI plus mu over r cubed times r crossed with HI. And that's still equal to 0. But we're actually going to find some interesting properties when we actually go through this, which we'll do now. So first, AI crossed with HI is equal to d dt in I of VI crossed with HI. But because HI is fixed in I, that's equal to d dt in I of VI crossed with HI. And you can see that because if I use the product rule on this last term, I get d dt in I of VI crossed with HI plus VI crossed with d dt in I of HI, but d dt in I of HI is 0, so I wind up getting AI crossed with HI. So that's how that plays out. So that means that this quantity, AI crossed with HI, can be written as a total derivative in the inertial frame of VI crossed with HI. So next, we can actually work with the second term, which is we've got mu over r cubed times r crossed with HI. Now that's equal to mu over r cubed times r crossed with, well, what's HI? It's r crossed with VI. Now you can see here that I have a triple vector product. So then recall from vector algebra that A crossed with B crossed with C is equal to A dotted with C times B minus A dotted with B times C. So that implies that mu over r cubed times r crossed with HI is equal to mu over r cubed times, well, I get r dotted with VI times r minus r dotted with r times VI. I just substituted into the vector triple product. So now we have this particular result, but we can actually use another result which will actually enable us to be able to figure this out in a slightly different way. So first, we're going to rearrange this equation, which is that recall that r is equal to the magnitude of the position, which is also equal to the dot product of r with r to the 1/2. So that implies that r cubed is equal to r dotted with r to the 3/2, from which we can actually write mu over r cubed times r crossed with HI is equal to, I can put this now in a big fraction, which is I get r dotted with VI times r minus r dotted with r times vi, all divided by r dotted with r to the 3/2. So this is the result we're going to start with, because we're going to actually find another way to be able to write this last result, and we're going to do that as we move to the next step. So rewriting the last result from the last page, we have mu over r cubed times r crossed with hi is equal to mu times r dotted with vi times r minus r dotted with r times vi, all divided by r dotted with r to the 3/2. Now what we're going to do is we're going to come up with an alternate expression. So we're going to do the following, which is consider the quantity r divided by r. And what we're going to do is we're going to take the rate of change of the position divided by the radius in the inertial frame I. So what do we get when we do that? So then d dt in I of r divided by r. What's that equal to? Well, we know that that's d dt in I of r divided by, well, as we said, the radius is the position dotted with itself to the 1/2. So now if I expand this out, what do I get? Well, this is now the quotient rule. So this gives the following. This implies that d dt in I of r divided by the radius is equal to, well, it's the derivative of the numerator, which is vi, times the denominator, which is r dotted with r to the 1/2, minus the numerator, which is r, times the derivative of the denominator. Well, the derivative of the denominator is 1/2 times r dotted with r to the minus 1/2 times the rate of change of r dotted with r, which is equal to 2r dotted with vi, and then that whole thing is multiplied out, and then we get divided by the denominator squared, which is just r dotted with r. So let's go through that again. It's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. It's the derivative of the denominator that's complicated. It's 1/2 r dotted with r to the minus 1/2 times the rate of change of r dotted with r. Now the rate of change of r dotted with r in the inertial frame is vi dotted with r plus r dotted with vi. But vi dotted with r plus r dotted with vi is 2r dotted with vi, which is how I got that result that we obtained. And you can see that the 2 and the 1/2 wind up canceling out. So this winds up giving us d dt in I of r divided by the radius is then equal to, well, if I cancel this out, what do I get? I get vi times r dotted with r to the 1/2 minus, and I get r dotted with r to the minus 1/2, and then I have times r dotted with vi, all divided by r dotted with r. Now that doesn't seem like it really helps a whole lot, but suppose I multiply the numerator and denominator by r dotted with r to the 1/2. Then what do I get? Then I get d dt in I of r divided by the radius. Now what I'm going to do is I'm going to take the numerator and I'm going to multiply it by r to the 1/2. So let's actually do that. So I get r dotted with r to the 1/2 divided by r dotted with r to the 1/2. And then it's multiplied by this original fraction, which I have here, which is VI times R dotted with R to the 1/2 minus R dotted with R to the minus 1/2 times the position times R dotted with VI, all divided by R dotted with R. So that gives me, now when I multiply this whole thing through, I wind up seeing that I get R dotted with R to the 1/2 times R dotted with R to the 1/2, which just gives me R dotted with R. So this gives me VI times R dotted with R. And then I get R dotted with R to the 1/2 cancels with R dotted with R to the minus 1/2, and I'm just left with minus R times R dotted with VI. So let's write that out on the next page. So we then have d dt and I of R dotted with R is equal to R dotted with R times VI minus R dotted with VI times R, all divided by R dotted with R to the 3/2. So then, multiplying by mu, we have mu times d dt and I of R divided by R is equal to mu times R dotted with R times VI minus R dotted with VI times R, all divided by R dotted with R to the 3/2. But that can be written as minus mu times R dotted with VI times R minus R dotted with R times VI, all divided by R dotted with R to the 3/2. So then, using the result from the previous page, that's equal to minus mu over R cubed times R crossed with HI. And you can then see from this result, we wind up getting that mu over R cubed times R crossed with HI is equal to minus mu times d dt and I of R divided by its magnitude, or the radius. So that gives us the two terms. Now we have both terms. So now we can actually put these results together, and we can get the final result that we're actually looking for. So we then have AI crossed with HI minus mu over R cubed times R crossed with HI is equal to d dt and I of VI crossed with HI, that's the first term that we had, minus mu times d dt and I of R divided by its magnitude equals 0. Now you can see that we can pull out the rate of change in the inertial frame out of the whole thing. So that gives us that d dt and I of VI crossed with HI minus mu times R divided by R has to equal 0. So now I have the rate of change of a whole vector has to equal 0 in the inertial frame. So that implies that what's inside the parentheses has to be fixed in the inertial frame. So this is VI crossed with HI minus mu times R divided by its magnitude has to equal C, and that C has to be fixed in the inertial frame. Now, the quantity C, or the vector C, is called the Laplace vector. Now, even though the Laplace vector is interesting because it actually turns out to be fixed in the inertial frame, we don't actually work with the Laplace vector. We actually divide through and normalize by mu. So normalize the last result by mu. And what that gives us is, it gives us VI crossed with HI divided by mu minus R divided by the radius is equal to C divided by mu. And this quantity is defined as E, and it's what's known as the eccentricity vector. So C is fixed in I, and that implies that E is also fixed in I. And we work with E instead of working with C. So now we have a second vector. So we just derived a second vector that is fixed in I. But remember, we're trying to develop a right-handed orthonormal basis, so we need to know whether or not that vector is actually orthogonal to the first vector that we derived, which we're going to do now. So we want to know if E is orthogonal to HI. So let's just take the scalar product between the two. So if I take E dotted with HI, I get VI crossed with HI divided by mu minus R all divided by R, the whole thing dotted with HI. But that's equal to VI crossed with HI dotted with HI all divided by mu minus R dotted with HI all divided by mu. Now we know that VI crossed with HI is orthogonal to HI. It has to be, because the cross product between any two vectors is orthogonal to both the vectors. So that implies that VI crossed with HI dotted with HI has to equal 0. So the first term is 0. And also, because HI is equal to R crossed with VI, that immediately implies that R dotted with R crossed with VI has to equal 0, because R has to be orthogonal to both R, the cross product of R with VI, because the cross product of R with VI is orthogonal to both R and VI, so therefore that's equal to 0. So that means that E dotted with HI is equal to 0, which implies E is orthogonal to HI. So now we found a second vector. And now this is really interesting because we can actually draw a picture to go with this. So here's the picture. I'm kind of going to add to the picture we had previously, which is, once again, we have our inertial frame. We've got O, which is fixed in the inertial frame. And that, of course, is where the central body is. We have this plane, which we've defined, which is the plane in which the solution lies. And then there's this vector, which is the specific angular momentum, which is normal or orthogonal to that plane. And then we have a vector E. And E lies in that plane. So E lies in the RVI plane, and H lies orthogonal to that plane. So somewhere in this plane is this position R, and then subsequently also the velocity VI. So they're both in that plane, and E is also in that plane. So now we actually have two vectors that are orthogonal to one another, so we can define a right-handed orthonormal basis. So we're going to say let HI divided by its magnitude equal PZ. And we're also going to say that E divided by its magnitude is equal to PX. Then that implies that PY is equal to PZ crossed with PX. And this basis, PX, PY, PZ, is fixed in the inertial frame I. And we can actually draw another picture to show what this looks like. So here's what this picture looks like. This is the solution plane, and here's point O, and then off to the right is the eccentricity vector, and then this direction is px. Pz is the direction out of the page, which also happens to be the direction of the specific angular momentum, and then py is the cross product of pz with px. And then in this plane lie this position vector and then the inertial velocity vi. So that actually provides a little bit more insight into what's going on. And this here is the plane of the solution. And of course it's fixed in I. So now we have a lot of information from which we can actually build upon. But the first piece of this information is actually looking at this diagram. We can see that there's an angle between these two vectors, between R and E. So nu is equal to the angle between R and E. And we're going to use that information to be able to derive a solution now to this two-body differential equation. So we know the following. So this is how we're going to start. We're going to say let E equal the magnitude of E, of the eccentricity vector. This is what's known as just the eccentricity. It's not a vector, it's just the eccentricity. The eccentricity vector is the actual vector. Its magnitude is what's called the eccentricity. So now we can actually take the dot product of R with E. And what we get is we get the magnitude of R times the magnitude of E times the cosine of the angle between them, which is nu. And so that gives us RE cosine of nu. So that gives us one expression for this dot product between these two. Now we're going to come up with a second expression for R dotted with E. So in addition, we also have that R dotted with E is equal to, well, it's R dotted with, well, what's E? E is VI crossed with HI divided by mu minus R divided by its magnitude. So let's work this out. We get R dotted with VI crossed with HI divided by mu minus, and we've got R dotted with R all divided by R. Well, R dotted with R is just R squared. So this gives us R dotted with VI crossed with HI all divided by mu minus R squared divided by R, which is just equal to R. So now let's work with this dot product. So we know, and this is again from vector algebra, that A dotted with B cross C is equal to C dotted with A crossed with B. So that implies that R dotted with VI crossed with HI is equal to HI dotted with R crossed with VI, just using that triple scalar product rule. But R crossed with VI itself is just HI, so this is equal to HI dotted with HI. Now we're going to do something else. We're going to say let H equal the magnitude of HI. Well, that implies that HI dotted with HI is just equal to H squared. So now I can substitute that in to this expression, and we get the following. So we then have R dotted with E is equal to H squared over mu minus R. But that has to equal the first expression that I had, which was RE times the cosine of nu. So now we can solve for R. And what do we wind up with? We wind up with H squared over mu is equal to R times 1 plus E cosine of nu, which gives that R is equal to H squared over mu, all divided by 1 plus E cosine of nu. Now, we often rewrite H squared over mu, so we're going to say let P equal H squared over mu, and this is what's called the parameter, and it's also called the semi-lattice rectum. So in terms of the parameter, or the semi-lattice rectum, we get R is equal to P over 1 plus E cosine of nu. And this last result is what's called the orbit equation. And as I said at the beginning, notice that the solution here is the radius as a function of this angle nu. And the angle nu actually has a meaning, which I'll define on the next page. So now, note that because R is equal to P over 1 plus E cosine of nu, R will be minimum when cosine of nu is equal to 1, which is the same thing as saying nu is equal to 0. R will be a maximum when cosine of nu is equal to minus 1, which is the same thing as saying nu is equal to pi. So now, given that the angle is the angle between R and E, so here's E and here's R, this now tells us that when we measure from the eccentricity vector, that angle, that when R and E are aligned, the spacecraft is going to be as close to the central body as possible. And when we're on the other side, when R is a maximum, that's when the angle is going to be pi. And that leads us to the definition. The angle nu is called the true anomaly. So nu is equal to the true anomaly. So then the orbit equation, R is equal to P over 1 plus E cosine of nu, is in terms of the angle called the true anomaly. So that takes us to the end of this lecture, and we can summarize this lecture as follows. So first, we stated the two-body problem physically, and then we derived the differential equation that describes the motion of a spacecraft relative to a central body. And then we solved this differential equation and obtained the radius as a function of an angle called the true anomaly, and finally we also derived key properties of the two-body problem that enabled constructing a right-handed orthonormal basis, a basis for E3. And that was all done simultaneous with solving the differential equation. So that takes us to the end of this lecture. And in future lectures, we're actually going to use the results from this lecture to be able to characterize different types of orbits, which we didn't do here. But we'll actually do that in the next lectures.